Yes, hello. So as mentioned, my name is Kamil Owczarek, and I'm a big data developer at GFT. And today I'd like to, I can refer to myself as a, say, survivor of multiple bad cases of big data systems orchestration. It was pretty rough in multiple cases. So my idea here today is to show you the knowledge I've gained about certain orchestrators and doing custom orchestration, this kind of stuff. So if you need to do it in your system, then you will have some basics, right? And the way I want to do it is I'll talk a little bit about what orchestration is in general, from like very simple stuff. Then I'll say how this is specific in the big data domain, and then we'll do a run through different ways you can do orchestration, from like a very simple ad hoc one through some popular orchestrators to writing your own custom orchestrator summary, and well, there's some ceremony, right? So orchestration, what it is? Well, I guess there has to be a Wikipedia definition in the beginning, right? So orchestration is an automated arrangement and coordination and management of computer systems. So essentially, when you have your system, you have some services or basically pieces of code working there. That orchestration, it manages how this is deployed, how this is placed on different machines, on in Docker, this kind of stuff, and how services communicate with each other. Pretty much, it's like a digital brain of your system. And uh, but from what I notice here, some of you definitely have a lot of experience with large-scale systems, so you know that some kind of orchestration, when you have a distributed system or a large-scale system, that's pretty much inevitable, right? And we're going to focus on two aspects, let's say, of orchestration. One, you can say this is arrangement, which is to say if you wrote your, say, microservice, right, and you have it in your Docker repository, then what you need to do is you need to have it deployed, you need to have replicas spawned, you need to have some kind of load balancing, port opening, this kind of stuff. And so generally what you do is you write some kind of descriptor like this one, and you put it in the orchestrator, which then constructs this kind of, let's say, small architecture for it, where you have load balancer, when you have the a few instances of your service spawned from the Docker image that you specified in the descriptor, etc., etc. And this getting your code to work in a proper setup, you can say this is the arrangement part of the orchestration. And then there's coordination. So say some client, whether that's like a physical person or another application, wants to access your service, they probably need to go through some kind of virtual route, right, which will then be proxied to the instance of your service, which then probably will contact some other services. That's let's just say in a microservice like kind of environment. And they will all go through the orchestration until the last communication is returned to the client. And that's managing how data is flowing through your system is more of the coordination part of orchestration. And in traditional systems, you would use different kind of stuff for arrangement, things like Kubernetes or Docker Swarm or Mesos, right? To get this deployment and to put your code in place with replication, all this kind of stuff. And then for coordination, and if you want to, let's say, streamline your workflow a little bit, you can use things like Kamil, all sorts of integration buses, some terrible BPMN engine probably. And yeah, this is the coordination part. And now since we've did a short run through what orchestration is in general, let's talk a little bit how this is specific in big data systems. First question in all big data talks is what is big data, right? They always say that when I mentioned that I do big data. So for this specific presentation specifically, I will refer to big data as something pretty much like this, right? So you have some system that revolves around Hadoop. You have probably Spark, things like Spark or Hive for processing, some NoSQL storages, HBase, etc., etc. Cluster manager in CRM, Mesos. You could say that this could be your average Cloudera, could be HDP, right? They all belong to this class of systems. And I'm not saying this is the only way you can do big data, but I'm saying this is the way I've always done it, and most of big data is probably done in these sorts of systems, right? And again, what is big data? Well, pretty much it's just data that you can't process on a single machine, right? You have so much data, you can't just put it on one machine and process it there. So you have to have, logically, distributed storage and distributed processing. You have to put it on a cluster. You have to process it locally as much as you can, because otherwise it wouldn't work. You can't just, pull it all to one machine and try to mangle it there. And so first conclusion is that big data orchestration needs to be compatible with highly distributed systems. That's like an obvious one. Let's talk a little bit about the arrangement part, because effectively what you orchestrate is your processing part, whether that's some old kind of stuff like MapReduce or Hive, or something more modern like Spark Impala jobs. This is what you need to put on your cluster, right? And in big data, that's specific because all those tools that you can see here, and pretty much every processing tool, adheres to this kind of code to data philosophy, which means that you basically you take your application, you subdivide it into parts, and you send those parts to be executed there where the data already is, because you can't afford the cost of network transfer, right? To transfer this data between nodes there where you have the code. Now you just send the code to where the data is. And that means that the arrangement part of orchestration, for the most part, in big data systems, is done under the hood via your processing engine, whether this is, again, Spark or Impala, etc. They usually take the cluster's resource manager, and they decide where your code is going to run and in which container and what time, right? So when you choose your processing engine, you mostly choose your arrangement, and then you just need to get your code to the processing engine. You could look at this schema, right? This is a very simple explanation how it works. You put your program into your master, whether that's like a Spark master or I don't know, running version of Impala, right? You put your jar or your SQL script. It generates some pieces of code which are sent to the nodes on the cluster where the data is lying, and effectively you do parallel processing of that data on those nodes, right? So in that way, in big data, mostly you need to get your program into the processing engine, and then the engine handles arrangement as the part of its work, simply because it's not indifferent how arrangement is done from the performance standpoint. It's actually extremely important. That's why this is a big part of, say, logic of Spark, right? How the code is subdivided and sent to nodes to be executed. And the second thing is data pipelines, right? So first of all, as the name suggests, your data sets will be massive. And they will also be messy, because in big data, you pretty much always pull from multiple data sources. You have your logs, you have some stuff from databases, you have some stuff in JMS, which probably isn't what you thought it's going to be. So you can't just start working with it. You have to do a lot of pre-processing, maybe correct the gaps in the data, pull the same data from two sources and try to reconcile it, do some kind of metadata enrichment. Before you actually can extract any kind of value from data, you have multiple steps. And you could think that you can just put it in one application, run it, done, right? But in practice, that would be like a dumpster fire, essentially, that application. No one would understand what it does, except for the person that wrote it, hopefully. But also not always the case if you do it like this. Usually, that would mean that no one would understand what it does. So what you do is you subdivide it into parts, right? You do the cleanup, maybe some second cleanup, some metadata enrichment, then you do some kind of joins, and in the end, you can, on this joint data, maybe you can do analysis. That could be like a real life example, right, of how data is being processed, especially in batch systems. But I think it's from my Spark training, but still, that could happen in real life. And not only there are like data dependencies between those pipelines, and you can see here, but also you usually also depend on a specific version or a specific timestamp in that particular data set that you depend on, right? So dependency management has to be a part of a, say, coordination in big data orchestration. Without that, you can't really do much. And the last thing that you need to know is that there is also availability, and fault tolerance is crucially important in our task, because, well, if you have massive transformations and they really do something meaningful, that usually a single transformation carries a lot of value. And if you automate systems, as was mentioned before by Jakub, I think, that's all good, but also has one funny side effect. People know that machines make less mistakes than people, subconsciously. So when you had some task say, some data processing tasks triggered manually by a person, and you have this person's manager that reads the report, they would probably always check the report if the person hasn't made a mistake, I don't know, entered wrong parameters, right? But when you automate it, what they're going to do is they're probably going to check this report 3 times and say, okay, the machine does it correctly, right? The 3 correct reports. So they're not going to check it anymore because, the machine is always right. Well, that's not always the case, but you have to make it the case in that if you make automation, you have to assume that people will no longer really check if it works correctly. So it should probably, your orchestration should never fail. And if you guide the process, you guide the pipeline, if it fails, because it eventually always will, even if it should never fail, right? It should at least bring itself back up and start where it left off, right? Because there is no, say, higher entity in your system than the orchestration, right? There is nothing above the digital brain. So it has to be extremely highly available and fault tolerant. Okay, so that, you could say, was all the requirements and specifics of big data orchestration and coordination outlined. Now let's see what are different ways to do it. And first, the story of my life, which is, often when you start a kind of big data project, there is a lot of hype around it, right? There's big data and all of that. And there are 2 ways people go about it in terms of orchestration and job coordination. Either they don't do nothing and they just write transformation, and then they run them and at some point starts working. It's like, why doesn't it work? Well, there was no data at the input, right? Then someone gets really angry. Or on the other hand, your architect went to a presentation like this, but he was hanging out on Slack or on Twitter for the most part, but he heard big data, orchestration, something. So say, well, you need to have an orchestration engine. Work on that for 2 weeks, right? And we will have cool orchestration. So you invest a lot of time in writing orchestration for your free Spark transformations. And it maybe works, maybe doesn't, but you spend more time on doing orchestration than on your transformations, and also everyone's angry with you. So my suggestion would be, if you're kickstarting a project, if it's a greenfield one, or you have 1, 3, 5 transformations, what you should do is you should do this ad hoc orchestration thing, where essentially you don't use a huge orchestrator, right? You just start your transformation, check if you have all the dependencies you need. If you have them, run it. If you don't have some of them, either wait and check again, or just report failure. As simple as that. If you have just a few transformations, that will work for you. Well, until your 5 transformations basically turn to 15 or then 20, then what you risk is that 1 transformation will not start because you made some kind of bug in the dependency checking logic. Then because of that, 3 transformations will not start, and then another 5 will not start, and you have cascade failure, right? So the good thing to do, from my experience, is to start with ad hoc orchestration, basically programs self-checking their dependencies, but then once the system gets bigger, take time to think about my more professional orchestrator. And that's still here. And yeah, one more thing I like to say, it's a very terrible thing, but also happened to me pretty much in any project. There was a point when they said, why don't you use that BPMN thing? It has nice UI, right? It represents pipelines, big data pipelines. So use that for orchestration. Or, we're going to put a WSO2 integration bus in there. It's going to do great. No, it's not. Because first thing, those things don't really have any kind of integration for the jobs that you're going to be doing with big data. No special integration for Spark jobs, Hive jobs, nothing, right? So what you're going to end up doing is you're going to have it as UI, and then you're going to write your custom orchestrator underneath anyway. So it's no use. And the other thing is, they're heavily focused on having all the control centralized, right? Which doesn't work with high availability. If you have everything centralized on one node, this is like integration bus 101, then if that fails, your whole system is dead and you're in huge trouble. What you can use, for instance, is things like Oozie. Oozie is the default orchestrator on many platforms. So the plus is that you pretty much always have it by default. If you buy Cloudera or you have Hortonworks HDP, you already have Oozie, right? It's kind of an old one. It's based on MapReduce, so it's kind of slow. But it has a good high availability setup based on basically, replicating, having multiple replicas on every layer in its high availability setup. And so it's really hard to kill, and if done correctly, and yeah, it just keeps working. But it also has a downside, namely, it's configured in the crazy verbose XML. That one literally just runs one Hive script, so already 15 lines of XML, and it only gets worse and worse if you write bigger pipelines, right? So this is really terrible. And on the other side, you have it, cool web UI, also pretty old and terrible. You have some ways working around it, like you can use Falcon on HDP, and that makes the UI thing significantly better. But still, Oozie is good for, in that it is on platforms. If you orchestrate legacy systems, it has good support for all the MapReduce, Hive kind of stuff, but it doesn't really support things like Spark or Impala very well. Actually, the plugins for that are pretty terrible. So I would advise to use Oozie if you don't need to think a lot about it, or you have a legacy system which is kind of a mess, and you want to put some order in there. Then you can orchestrate your flows in Oozie. That's gonna work pretty well. But then maybe Azkaban. It's another orchestrator which was developed by LinkedIn, and also specifically for big data type of systems. It's better than Oozie for the most part, although you mostly have to install it yourself. It has a architecture which is heavily based around plugins. So it's kind of like Maven. You have a small core, and pretty much everything else, job types, triggers, viewers, are plugins. And it has, on one hand, you have good support for this old-timey jobs like pig scripts or Hive scripts. But on the other hand, the Spark integration and things like that are also pretty decent. So you can do legacy, you can do modern. It's not shipped with those platforms like Cloudera or HTTP, so that's kind of a minus, but not a very huge one. But it also has a good high availability setup, pretty much done in the same way as Oozie does it, as we've seen on the slide before. It has a slightly better UI and the way of configuring things. It doesn't rely that heavily on XML. You can put bundles in there, which you can then nicely store in, say, version control. So that's a plus. And yeah, here you have just a screen from the UI. It looks a little better than the Oozie one. Though maybe I should have shown something more extensive, right? But it's definitely more user-friendly and definitely friendly for, some business people who would construct those pipelines for your elements, for instance. And then when talking about orchestrators, I want to mention something that's not really orchestrators per se, though they like to refer to themselves and people like to refer to them as orchestrators for some reasons, which is specifically the job runners that you have for Spark. And again, I'm saying job runners on purpose because they don't do full orchestration, as you'll see. And these are things like Livy server, like Spark Job Server, or the new one, which I've recently checked out, which is Hydros Firmist. Has anyone heard of that? It's worth checking out. But one thing you'll immediately notice about those things is they all have a lot of common parts in that you work with them in a pretty same way. So the basic goal is to present the Spark transformation as a function and to make the transformation more reusable and reconfigurable. So to do that, you have to, in your main class, where you have where you run the Spark project from, you have to implement some kind of their interface. And here you can see an example of how this is done in Mist, right? Where you have to extend this Mist FN trait and declare the arguments. Then you can do processing based on Spark context in this example, and you can return a value. So you have your Spark code represented as a function, right? You can take arguments, you can return values. That's pretty much how all those do. So Livy has its own interface, but it essentially does pretty much the same thing. And the Spark Job Server has its own interface, which pretty much does this thing as well. And the interface, all of them also have interfaces for Spark in Scala, Python, and Java, which, well, that's pretty good. And once you have implemented that interface, you can build your jar and use HTTP and HTTP endpoint to deploy it. So you have it deployed on the job server. And then from that, you can run multiple jobs, multiple transformations in the way that each time you can provide a different configuration. So again, your job is reconfigurable. You deploy it once, and then you can run it many, many times. And yeah, the job can return results that you can then mostly retrieve through HTTP. And yeah, I've shown you that already. And here you have also an example from Mist, where you have those two endpoints. The first one would be for deploying the jobs, right? And then you will have to send the jar there via HTTP. And then the second one you would call with the configuration to run a job from that jar. And all of those also support something which is kind of important in Spark, is that you can share contexts between jobs, for instance, right? So you can have a context which is heavily utilized, and in that way you get better performance, which again is kind of key in Spark. And so for the most part, those three are very similar, but each one of them has some kind of killer feature, you could say, by which you can probably make your choice between one or the other or the other. And the killer feature for Livey would be that you can actually send raw code to it for experimentation. And essentially you can send code as text in HTTP. And if it compiles to regular Scala code, you can actually have it run on the cluster through Livey. So in case you have some, say, security restrictions on your cluster and you can't do interactive mode or you can't access Spark Shell, you could probably use Livey to do some necessary experimentation, as a feature for your data scientist, let's say, right? If you don't have a notebook on that cluster again. Spark Job Server, here the stuff is slightly more serious. I actually kind of like this feature in that you can declare named RDDs or data frames. And this is essentially a way of passing references under the hood between multiple jobs. So you can create an RDD in one job, right? But then it would, if you run the second job on the same context, because we have context sharing, we'll be able to access the reference to that RDD. And that's good on one hand, but it's still done under the hood. So what you're risking here is that you might try to access an RDD which doesn't exist because there was a bug in a former job, for instance, and Spark Job Server doesn't do dependency management as such. Again, it's just a job server. And the other thing is you might, just create a named RDD which is going to hang in there, but no one's going to access it. So it will essentially, bloat your memory for no good reason, right? So it's supported, but it's not part of this, a Spark transformation as a function interface, which really means that you can still make a lot of errors with that. And Mist, again, it has one very distinctive feature, is that you don't have to run all the job instances, all the jobs from a particular deployment through HTTP, because you can do that through Kafka. Essentially, you submit a JSON to Kafka, and then the server can take it and go with it from there, which is a nice feature because if you think about it, with Kafka you can do things like at least once delivery semantics. So you can nicely cluster Mist through Kafka. You could have, if it supported consumer groups, which it still doesn't, but should support them in next versions, meaning that they have open tickets for adding support for consumer groups. So then you can imagine that you could essentially cluster Mist and run your transformation with at least once delivery semantics, which means that you would never lose a job. And yeah, so those runners, again, they are good for job reuse. They are good for parameterization. They have some nice specific features. What they don't do dependency management. They don't have any kind of high availability setup by default. So they're not proper orchestrators. However, you can easily imagine, like with the Mist example, that you can take those job runners and work around them a little bit to easily, add things like high availability setup with some kind of proxy, right? You can work out dependency management and just plug it in to this via HTTP. So there are a good basis to easily build an orchestrator solution should you need to do it. Yeah, and about building your custom orchestration solution. That's like an old slide from I think it was Scala Wave last year, but it's still relevant, so I really wanted to put it in here. Well, we probably all still freshly remember that Marvel did this thing, right? Where they did those Thor movies and Iron Man movies kind of in one universe. And it really clicked. It earned them a lot of money, and then it spawned the Avengers franchise with the Infinity War movie. It was pretty awesome. And then what happened is that all the other Hollywood production studios, they thought, oh yeah, the cinematic universe is such a great idea, right? It earns a lot of money. So we're also going to do that. And you had the DC universe with Batman versus Superman, and this awful like Suicide Squad movie. All right, that was slightly awful, but then at some point, I don't know if you remember the movie, the Mummy movie. It was really kind of terrible because what it did is they wanted to make this dark universe where we like Dracula with Mummy and Frankenstein monster would have their kind of shared universe franchise thingy. So why the movie was so awful was essentially that the movie had no plot, right? They only focused on referencing those other movies that would not be made anyway, and universe building, but they didn't focus on the purpose of the movie, which is kind of to entertain viewers, right? And so I find this really analogous to some stuff that happens in IT very often, especially if you have projects that have a lot of senior architects that you're pretty much guaranteed to have that, is that you buy yourself a distribution of, let's say, Cloudera CDH, or maybe Mapper Access, or maybe HTTP, right? And then your architect tells you, we're building a data platform for our bank, right? Or you're building a data platform for our organization. And so they start planning stuff and they say, okay, so here we'll create a dependency management tool, and here we create an orchestrator, and here we have a data catalog, right? And that's like the universe building thing with the Mummy, right? That they focus on building a platform for the reason, of saying we've built a data platform. But you don't really need to do that because you already have a data platform. CDH is a data platform. It has a data catalog, right? It has an orchestrator. Same thing with HTTP. So my message here would be, try to push back against this type of stuff, because for the most part, you already have those tools and you don't have to implement them, re-implement them. And that's the thing with orchestration too. Because why am I so keen on that? Well, because we've built a custom orchestrator. I've built 2 of them in 2 different organizations. Both worked, but both were kind of terrible. And having said that, there are some legitimate reasons sometimes to actually build a custom orchestrator. For instance, one reason would be that you need to support some specific types of jobs, and that was our reason, because apart from doing things like Spark, we also had jobs in the Spring Batch, pretty much legacy stuff. We had Akka jobs which were more fit for Akka streams because we needed that back pressure really badly, and Spark doesn't have back pressure. And there were also exotic things like Informatica, which we had to have in our systems until we could rewrite them for like 2 years. So, you can't really support Informatica jobs, I believe, with things like Oozie or Azkaban. So we had to write it custom. You might need to have a very defensive high availability setup, something more than you really have when you just have 3 instances of a server running on 2 round-robin instances of a SQL database, right? You might want to integrate with very specific external systems in your company, and that's also kind of one of the reasons why we did the custom orchestration thingy. And then dependencies. Well, that's a weak reason, but you might imagine, for instance, that you might want to have circular dependencies, which would make a few circles if some measure is not met. That thing you can't really do in things like Oozie or Azkaban, and I don't think you can write a plugin that would do that, because they implicitly want you to have a directed acyclic graph of dependencies, and that's it. So these are some reasons you could have. And what we did is we designed this kind of architecture, where our orchestrator was essentially also a small cluster of its own. So we had multiple instances of our orchestration, each one with the common definition of our pipelines on it, and they were all connected with, let's say, a communication bus, which, when the data appeared, when you had a new data set that could potentially trigger a transformation, that was verified by a small external application, and it submitted a message to the communication bus, which then assured that only one of the orchestration nodes would receive a message about the need to run the transformation. And then what it did, it took the pipeline's definition and it worked with it and with the cluster to process the data. On a smaller scale, it worked like this. The orchestration node worked through the stages. It had some metadata saying, this stage is an Akka Streams job, this stage is an Informatica job, this stage is a Spark job. And it contacted the specific executors for those particular jobs, and they were run here. And technologically speaking, for all these communications, a communication bus here, and this separate communication between the orchestration node and the executor node here, we eventually used Kafka, for the reason that we could do custom acknowledgements, and we could do we could do at least once delivery. So we, after consideration, we decided to do at least once because we could assure that our transformation with this orchestrator, no transformation would ever be lost. However, in bad conditions, it could happen that one transformation would be run twice or even more, right? Which is still bad, but not as bad as losing transformation for that particular use case. Might be different in your use case. And so we went with Kafka, but initially we implemented the orchestrator working nodes in Akka cluster, and they were all connected via the cluster, as well as the jobs, the nodes that would run those particular transformation, like a Spark transformation or Akka transformation, were also part of the cluster. It was fine, except it wasn't, because Akka cluster it's a really great framework for clustering. It's really fast, but what it has kind of problems with is things like split brain scenarios, or when when your node fails in Akka cluster, it cannot rejoin with the same ID, so it has to acquire a different ID, and you wouldn't know that this node with this identity came back up. It's really difficult to make. So we changed Akka cluster to an application that worked on Akka actors. So each, say, pipeline execution was an actor that then spawned sub-actors that did particular stages. That's a nice, technically nice thing, because you can, for instance, do parallel executions of different parts of your pipeline if they're independent. However, yeah, we decided to distribute the workflow via Kafka because with Akka cluster, it is kind of difficult to, for instance, maintain node identity after node failure. For the trigger, we had a small external program, and for orchestration and execution communication here, that was also Kafka, right? For the reason of, for instance, having acknowledgements and receiving responses. With at least once delivery semantics being implemented globally. So throughout the whole thing, you had pretty much at least once delivery guaranteed. And the result of this was this. Well, firstly, the result wasn't great because we had the Akka cluster problem. And again, I know this can be solved, for instance, with things like downing providers, right? You can avoid split brain, and you can also work your way around the identity thing. But it isn't easy, and for good downing providers, you pretty much have to buy them from TypeSafe, which our organization refused to do. So we changed the workload distribution method, and finally it worked okay. You had nice UI monitoring, but the maintenance of this kind of architecture is still difficult as hell. And as well as you can see here that you have to have the same logic on all the nodes for that to work, right? Because no matter which node can pick up the job and process it in the same way. So deploying new versions of that logic, new versions of the pipeline to production was also kind of a pain because you were in constant risk of stop the world event. Again, this is all probably available, but you're not always that smart when you design it. And so my conclusion is, if you only write a custom orchestrator for big data systems when it's really necessary, because if you want to meet all the goalposts, support different types of jobs, be very highly available, very fault tolerant, etc., have a good control of your pipelines, it's gonna be really difficult. And 90% of the cases you can do with probably Azkaban or Oozie plus Falcon, or maybe with a job server and some additional code, right? And let me just quickly recap what I've said. You guys are still not sleeping, right? I should have, but I thought I could put since this is before lunch, I could just put random slides with like tasty food in here, and that would just like, I should have done that. Damn it. But yeah, orchestration, right? It's essential in all large-scale distributed systems. The first part is arrangement, and in big data, you mostly have it done under the hood by your processing engine. Why? Because it's essential for performance, and they just need to do that. So you mostly care about what processing engine you choose for performance, what type of cluster you choose, also probably for other reasons than orchestration concept, and then you kind of have it delivered for you. In big data, we have highly distributed systems. We have to be aware of that, very fault tolerant, and orchestration pretty much cannot fail. And if it fails, it has to pick up where it left off. And my suggestion would be, for small projects, when you start them from scratch, start with ad-hoc orchestration, just small tiny piece of code that checks dependencies and decides whether to run. And then while you have it and it's still working, think about something different, something more advanced for when the system becomes more advanced. In most cases, you can rely on those ready-made engines like Oozie and Azkaban that you have on your platforms, and there's no need to write custom orchestrators for every single, our data platform that we have in our organization. So just push back against this. Check what your platform has to offer first. And Oozie, again, it's old, it's inconvenient, but it's pretty much on every platform. And if you have legacy jobs, Oozie is probably the way to go. If you have a heavy system that uses a lot of Spark, etc., yeah, maybe take Azkaban. It has better support, it has better UI, requires some legwork to install, but definitely worth it. And then also, let me quickly recap the part about how, Spark, there are those Spark job servers, which people like to call orchestrators, but they don't really do orchestration in that they don't have, high availability setup, they don't have dependency management, but they're good for reusing Spark jobs. They have some very interesting features to be very hard to implement manually, so you can take those. And, by adding these missing features, you can have a nice orchestrator without doing that much legwork. Custom orchestrator, from my experience, again, it's very hard to do it correctly. Only do it when you really need it. And that's a bit early, but I guess that's good, right? So last slide, please rate the talk using the conference app, and only positive reactions, right? Are there any questions? Nothing. Yeah, I've seen that happen. Like people use NiFi for flow management and orchestration. And it worked okay, but you have this thing in NiFi where it does it pulls stuff to memory, right? Certain data sets. So if you say you want to do, I don't know, some preprocessing in Cassandra and then put it through Spark, that's going to be kind of confusing for NiFi, I guess. But I know that like Hortonworks were working on making NiFi kind of like the orchestrator for their platform. So I've seen it work, but there is this conflict where you don't want to do, processing in your orchestrator, right? You want to control the flow. And say if you're doing NiFi tasks on things like Cassandra, for instance, or Hive, it pulls data essentially to the memory as the flow file, right? And then you kind of have to save it and only then connect Spark to it. So can be done, but also has some quirks. But it's good we used it as an ingestion platform, and for that it works really well. Oh yeah, I heard about that one, but to be honest, I don't have that much experience with Airflow. I heard it's nice. So,
but there is a lot of bugs in Jira of that project, so we are wondering if it gonna be developed more.
But there was someone who, like, yesterday or 2 days ago, told me about Airflow that they had. Oh yeah, so yeah, maybe you guys can talk and about Airflow, right? Because yeah, Airflow I haven't used, sadly. Questions, anyone?
Which tools do you use to DR?
Two?
To make DR? DR, disaster recovery of Hadoop cluster.
Oh, well, let me think what's been used. So, yeah, I'm not sure about that since we had a cluster which last time I worked on that, it was like a managed cluster which we kind of rented from another branch of our company. So this type of stuff they handled. I know that's a terrible response, but kind of a true one.
Okay. Dziękujemy w takim razie bardzo. Brawa, proszę.